Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for high school students. In this video, I want to tell you about the difference operator, which can be thought of as the discrete version of the differentiation operator. And it's very, very useful for studying sequences, much the same way as the differentiation operator is useful for studying functions of a polynomial variable. Okay, to start off with, we'll consider two sequences, f and g. But to emphasize the analogy with functions that you see in calculus, I want to think of these as functions. Functions from the set of natural numbers n here to, let's suppose, the complex sequences, so to c. So what do I mean by that, and how does that give rise to a sequence? So suppose you have f is a function from n to c, and then what's it determined by? It's determined by all its values. So what are the values of f here? So you can look at f of 0, f of 1, f of 2, and so forth, right? And these values are all complex numbers. So here we just get a sequence of complex numbers. Okay. So basically, when you're in school, often you write a sequence where you'll have a letter like f denoting the sequence, and then you have subscripts. So basically, all I've done is I've changed the subscripts, those indices down below, to arguments of your function. And this will allow us to think of this as a function. So we can use function here to study these things. Okay, so we'll have two functions, f is this one here, and g will be another function, which will give you the sequence g of 0, g of 1, g of 2. Okay. So what's the first thing that you can do once you have this sort of viewpoint? So the first thing is that you can always add functions pointwise. So we can do the same thing here. So given two sequences, I'm going to give you a new sequence called f plus g. Okay, so as a new sequence, that just means a new function from n to c, sequence of complex numbers. So I just have to tell you what's the value of any natural number n. So what you do is you look at the nth term of the sequence f, so f of n, and you just add that to g of n. Okay, so that gives you the nth term of this f plus g. Similarly, suppose now you have some constant, right? So this constant will be just a complex number, c. So when you have a function, you can scale that function by any scalar that you like. And we can do the same thing with sequences here. So cf is going to be a new sequence. Okay, so what's its value at n? I'll just have to tell you what that is. So what I do is I look at f of n, and I just multiply that value by c. And that gives me the okay, so now with that, that's the viewpoint I want to take in sequences as functions. Now we can introduce the difference operator. And the difference operator, so you should think of this as the analog of d dx, or the prime that you see in Newtonian notation, and it's denoted by delta. The delta is chain. So the operator, this word here, means that it's a type of function, but the inputs are functions and the outputs are functions. So here, the functions that we have will be sequences. Okay, so we'll have a sequence of this f here, and this delta f is going to be another sequence. So it's a function from n to c. What's its value at n here? So what I do is I look at f of n plus 1, and I subtract f of n. Okay. So certainly this gives you a function from n to c, and hence a sequence of numbers. Okay. So what is this? So if you're thinking of these as numbers in your sequence, okay, so this is the term corresponding to n, this is the term corresponding to n plus 1. You're looking at just consecutive differences between numbers in your sequence, and hence the word difference operator. So remember differentiation, what's that? That's the difference quotient when you take the limit of them. Here, you can't take the limit as your arguments get smaller and smaller. The closest that you can get in your inputs is 1. Okay? So neighboring elements or numbers in the sequence. You can take the difference of that. Okay, so this difference operator, okay, what it does is it takes a sequence to a new sequence of differences, and this has many properties that are very, very similar to the differentiation. First thing is that if you differentiate the sum of two functions, you'll just get the sum of the derivatives. Well, here, if you take the sum of two sequences, okay, and you take delta of that, what you do is you take this new sequence, delta f, this new sequence, delta g, and the brackets, you ask the two sequences now. And these two sequences we can add according to that. I won't prove this, it's quite easy to prove. But you can do this as an easy exercise. Okay. Similarly, you know that when you try to differentiate a scalar multiple of some function, you can pull that scalar out. The same formula works here. You can pull this scalar out to get c times delta. In other words, if you look at the sequence, the new sequence c of f, what is the difference operator applied to that? What is that sequence? What you do is you look at the sequence delta f, and then you scale that by c. Let's see why this is true. So let's work out what is the value of the right-hand side at n. Okay, so the value of the right-hand side at n is, well, what does this say? You look at the value at n, which is just this one here, and you multiply that by c. So it's c times what you see here. C times what you see. But what about the left-hand side? The left-hand side is that firstly you scale f by c, and then you look at this formula for the scaled version. So you have to replace f by c out here. So basically you have c times this term here minus c times that term right here, which of course is the same as c times this difference. And that's what you get. Okay? So B is quite easy to prove. And A follows by a very similar argument, just looking at the definitions of the difference operator and how you add sequences. Okay, so the other thing that really makes the analogy with differentiation is part C here. Okay, so what you know from the fundamental theorem of calculus is that differentiation and integration are opposite. So here, taking consecutive differences, what's going to be the opposite of that? Well, it turns out to be a discrete version of integration, which we should think of as partial sum. Okay, so the opposite of taking a difference is to. So suppose you have delta of f is equal to g. Okay, so what do you have then? Okay, so you have delta of f equals g. Then what does that tell you about the actual values of f? So if you look at f of n minus f of 0, this is going to be this partial sum of these differences of these g's. G of 0 is g of 1, all the way up to g of minus 1. So why is this true? It's very easy to see why this is true. So what are all these g's? These g's are just the differences between consecutive terms. So if you sum up all the differences between consecutive terms going from f0 up to n, you'll get the total difference between f0 and n. That's what you see. Okay? So the analogy with calculus is, suppose that you know that g is the derivative of f. Then what can you say? Then you can say what the difference is between two f values, okay, by integrating. So the version of integration is actual sum. So normally you take the integration, it's the limit of Riemann sums, and you take the actual sum. The final thing, which is very useful when you need to do this process of taking the inverse, so-called inverse of the difference operator, is the following. So suppose delta f equals delta g. How different are f and g? Well, you know that if you have two functions and their derivatives are the same, then they differ by a constant. And the same is true here. Okay? If delta f equals delta g, then f minus g equals constant. And the way to prove this is very, very simple. Okay, so why is that true? So firstly, let's suppose you put c equals minus 1 here. That tells you that delta of the negative of a sequence, or the negative of a function, is just a negative. So now, that means that if you apply, instead of with g here, you replace it with this minus g. Okay? Delta of f minus g equals delta of f plus delta of minus g, and you can pull the minus sign out to see that delta of the difference is the difference of the delta. So if the difference of the deltas is 0, then the difference, this delta of this f minus g equals 0. And what does delta of a function equal to 0 mean? Okay, so delta of a function equals 0 means that this term here is 0. That means that the nth term and n plus first term is the same, and this is true for all n. In other words, they all have the same value, so it's constant. Okay, so this is the upshot of part D. Okay, it's quite easy to see from parts A and B. You can also prove this directly too. And that's not bad. Okay, so to sum up, if two sequences are such that when you apply delta to them, same, then they have to be the same up to some additive. Okay, so let's have a look at a quick example of the difference operator here. We're going to look at fkn is going to be my sequence. It's a sequence defined as follows: the function of n. This k is just some natural number, and I'm going to define it to be n choose k. So k can be any fixed natural number, 0, 1, 2, and so forth. Okay, okay, so let's be more precise about this. So this should be a function of integers, okay, which are non-negative. Okay. So you can rewrite this. This is the way I want to rewrite it. It's 1 on k factorial times n minus 1 times all the way down to n minus k plus 1. Okay, so this is clearly a function of n, or any value of n actually, but we'll just be looking at this in the case where n is going to be some non-negative integer. So in particular, if for example n equals 0, even if n is less than k, minor and it's 0 there. The other thing to note about this is what type of function is this of n. Okay, so you're multiplying k linear terms. So this is a discrete k polynomial. Okay, so let's see what this difference operator does to this sequence here. Let's look at delta k. It's a sequence, so we want to look at what's its value at n. So what you do is you look at the value of this sequence at n plus 1, so that's 1 choose k, and you subtract from it the value at n. So this n plus 1 choose k minus n choose k. And you know very well what this is. This is just n choose 1. And the good thing about this is that this is basically just the next function down. So this is f k minus 1. So that's a very, very simple example of how the difference operator works. Okay? You have a sequence of numbers given by this degree k polynomial. You take the difference operator. You get a new sequence. You get this sequence here, fk minus 1, which is now a degree k minus 1 polynomial. Okay, so there's the example of the difference operator works. But how do we actually use it to study sequence? So I want to have a look at this application. So this is a sequence that I want to have a look at, and maybe you've seen this before, but usually this is not so easy to work out. Okay? So what I want to do is basically look at the sums of those three squares. F of n will be 1 squared plus 2 squared all the way up to n minus 1 squared. Okay, so I guess this should be a function of non-negative numbers, so we need to know what its values are for all n. Ones which may not be so obvious is when n equals 1, what happens? When n equals 1, when n equals 2, right, you get 1 squared, so this last term is the same as the first term, so you actually end up with 1 term, 1 squared, okay? And when n equals 1, though, this will be 0, so basically you won't have that 1 squared, you'll have the empty sum, so you should define that as 0. And then the default value for f of 0, I'm going to set to be 0. We'll see in a moment why that's the but we'll just take that as part of the definition. Okay, so it's a very good question. Okay, what is the sum of these first m minus 1 squares? Okay? And maybe you know the answer, but I want to show you a way of getting at the answer, which is very pretty, using just what you see here. So in particular, it uses difference. And the thing that you should kind of see here is that, well, when you try to differentiate, for example, x to the n, okay, the derivative of that is something of a similar form. It's n times x to the n minus 1. And that allows you also to do the reverse. It allows you to integrate. And we're going to use this example here in a similar sort of way. And when you take the difference operator of fk, you get fk minus 1. So if you want to invert and do the discrete integration and try to integrate fk minus 1, you will get fk up to some constant. So there's always this. Okay, so let's have a look and see what we're going to do. So the first thing that we'll do is we're going to look at delta f. Delta f. So this is f of n plus 1 minus n. And that's just the definition. Okay? F is this sequence here. If you evaluate at n plus 1, and at n you get the same things except for in n plus 1 here, you have an extra term which is n squared. Okay? So this is just n squared. Okay, so that's what delta f is. So this sum is not so easy to understand, but when you apply delta f to it, it is. It's just n squared. And so now what we want to do is we want to get back the original f, so we want to try to do a discrete integration of it. Okay? And as is, it's not so easy, but the case that is easy is this one here. Okay? This is the case where we can discrete integrate. So I'm going to rewrite it. So what I'm going to do is I'm going to rewrite this n squared as. Firstly, something close to that is n times n minus 1. So that's n squared minus n. And then, so you've subtracted this n here. You need to add back an n to make sure. So why is that a good way of writing it? Because if you write it like this, well, if you look at this term, this is basically just this case here, okay, where k equals 2. So you only get these first two terms. Okay? And you don't have this 1 or 2. So this is 2 times n choose 2. And what about this term here? This, of course, is just n choose 1. So that's what you have. Okay, so now we've written it in this term, and now we just discrete integrate. And we're going to use part D. So therefore then is equal to, we discrete integrate this term, so remember what happens. Okay, the discrete integral of this n is k minus 1. It's basically n choose k up to a constant. So we just change this n choose 2 to n choose 3. And then n choose 1, when we discrete integrate that. And the other thing that you should do is you should check the constant term. Okay? And then, so let's just check the constant term. And the constant term here, what you do is you look at 0. F of 0 is equal to 0. And if you put 0 in here, both of these, you get 0 for both of them, so we don't have to. Okay, so I should now mention why was it that we chose f of 0 to equal 0. So this is very, very important. So the reason is as follows. Okay, so I wrote down that delta of f n to squared. And you should check that this is true for all values of n. So if you use this formula, okay, then it's certainly true for those values of n. But for 0, you have especially chosen some value for it. So we should check separately at 0 that this still falls. So what happens at 0? So at 0, delta f of 0 is equal to f of 1 minus f of 0. So that's 0 minus 0. And is that indeed, because n equals 0 here, 0 squared it is. So that's why we chose f of 0. So that this delta of f of n always equals n squared for all values, then even n equals 0. Therefore, bigger values, 1, 2. Really, you can just use this formula. Okay, and so the correct thing to choose for level 0 to make this formula work all the time. Okay, so here's a formula. Let's just see what it is, so we can write it out a little bit nicer. So the way we'll do that, and then you can see a very beautiful formula for this. So firstly, I guess you've got a 3 factorial on the bottom here, so let me just pull that out. There's 3 factorial. And then I'll put the 2 here, and then I'll have this sort of product of linear functions of n. And 1, 2. And then what we'll have is that we should have a half here times n minus 1. So the half is 3/6 of the 3 here, and then there's the n times n minus 1. Okay, that's what we have. And now what you can do is you can rewrite this term. There's a n times n minus 1 factor in both of these. And so what's left, once we've taken out the n and the n minus 1 terms, we've got 2 times n minus 2, so you've got 2n here. And you've also got 2 times minus 2 is minus 4, and you have to add 3 to that. You've got 1. Okay, so it's minus 4 plus 3, that gives you your answer. So it's a beautiful way to get this result. Maybe you've seen this before. If you want to sum the squares 1 squared, 2 squared, all the way up to n minus 1 squared, your answer is going to be a function of n, of course, and it's here, you can see it's a cubic function of n, 1/6 times n plus n minus 1. Okay, so let's just check some values for n equals 0 and 1, you get 0. For n equals 2, what do you get? You'll have 2 times 2 here is 4 minus 1, that's 3. 3 and 2 minus 1, so that's just 1, so that's still a 3 here. 3 times 2 is 6, 6 on 6 equals 1, so that's the 1 squared term. And of course, this will give you the formula in general. So I hope you found this example interesting, and now you can also use the difference operator to study sequences.